Hi, welcome to Teach You Why. Today will be the first ever chemistry paper walkthrough, which was requested by one of you here. If you do like to have any paper walkthrough requests, please drop me a DM on my Instagram account and I will try my best to work on your request. So today's walkthrough will be for the Assumption English School Pure Chemistry Paper 2. And as usual, the link to download the paper will be as shown in the description below. If you like more of this content, please subscribe to my channel and also follow me on Instagram. So without further ado, let's get going. Alright, so let's take a look at the first question of this paper by Assumption English School. So it says, which substance can be used for galvanization? So this should be quite a straightforward question. It will be zinc. Alright, there is no other metal there's typically no other metal that we use for galvanization. Which substance is added to the soil to reduce acidity? Okay, so to reduce acidity, we need to look for not a basic oxide. So in this case, we have calcium oxide. Alright, so CaO. Which substance is an element with giant molecular structure? Now, in this case, you guys only learn two types of giant molecular structure: silicon or diamond or graphite. Okay, so in this case, there's no silicon, and diamond and graphite basically are just carbon. So the answer is carbon. C. Which substance is a component in the alloy brass? So for brass, you just need to know that it's made out of copper and zinc. So it's copper. Alright. Which substance contribute largely to the air composition? So now air composition, you have your nitrogen, oxygen, and others. Alright, so the largest composition by now you should know is 78% nitrogen. So answer is N2. Okay, pretty straightforward question 1. So let's take a look at question 2. Okay, question 2. 4 substances undergo different chemical reactions and observations are recorded in the table below. So we have copper nitrate and substance 1, substance 2, 3, 4. Alright, so we are basically working on some Sudoku, so to speak. So let's see. So when substance 1 react with substance 2, a soluble salt is being formed by titration. Okay, so if you have titration, it means that this is also soluble. Okay, this is one of my clue. When substance 1 reacts with substance 3, effervescence, insoluble white precipitate form, reaction stops quickly. Okay, not too much information we can think about. Effervescence means bubbles. What kind of bubbles? Maybe it could be CO2, it could be H2. White PPT. So white PPT, what do we have? We just have to have some note on this. But so far, still not much we can talk about. Lighted splint extinguished with a pop sound when substance 1 react with substance 4. So the very obvious, this is hydrogen, and the only time you learn that when two substances react together gives you hydrogen is when this is an acid. So this is an acid. Alright, so this is probably a metal. So only when you have an acid plus metal, it gives you your H2 plus salt. Okay, so I'm very sure that substance 1 is an acid. So let's see what acid do we have. Okay, so sulfuric acid. Alright, so the substance 1 definitely is sulfuric acid. Uric acid. Okay, substance 4. Substance 4, we can choose between magnesium and silver. That is the only metal that we have. But in this case, I will choose magnesium because silver does not react with acid, as silver has a very low reactivity and is below hydrogen. If you can recall your reactivity series for metals, you will remember that silver is below hydrogen. Any metals that is below hydrogen, for example, copper and silver plus gold, okay? So your reactivity is as such. Okay, so anything that is below hydrogen, such as copper, silver, and gold, they do not react with acid. So that's why my answer would be magnesium. Okay, so in this case, we know that we are able to tell something. So substance 3. So in this case, effervescence, like I said, so if an acid, what other acid reaction that give bubbles other than hydrogen? So definitely not hydrogen, so I cross out. So in order for you to produce your carbon dioxide, it needs to have a carbonate. Alright, it needs to form a carbonate. So let's see, we have sodium carbonate and barium carbonate. Now the key word is a white precipitate will be formed. So what happens? So my answer, I'll give you the answer. The answer will be barium carbonate. Now, why barium carbonate? Is because BaCO3. So let's take a look at this equation. When sulfuric acid reacts with barium carbonate, it gives you your barium sulfate plus CO2 plus H2O. Now, which means in this case, right, this is your white precipitate that you should know. Okay, so what happens is that, let's say I have a piece of barium carbonate, all right, and then what happens is that the sulfuric acid comes in contact with this. It forms actually a layer. I hope I can draw something like a layer. Okay, layer of white PPT, and this layer is actually barium sulfate, and hence once you have covered the surface of barium carbonate, the reaction stops, which explains also why the reaction stops quickly. Okay, and hence we have barium carbonate. Substance 4. Oh, sorry, I made a mistake. Substance 4 is magnesium. Okay, I hope I don't confuse you guys. I was referring to substance 4 and not substance 2. Okay, so substance 2, soluble salt formed by titrating substance. So both substance 2 and substance 1 needs to be soluble. So let's see what we have that is soluble. Soluble will be sodium hydroxide. Okay, so why sodium hydroxide? Because all sodium, potassium, ammonium salts are soluble. Okay, sodium hydroxide. Okay, apologies for the swap just now. Okay, moving on. Question 3. Aqueous potassium manganate 7 can react with aqueous hydrogen peroxide according to the equation. Okay, so we have this equation. So complete the table and see. Let's see. Oxidation state of manganese in potassium manganate is 7. Okay, of course, because you have a 7 here. Manganese sulfate. So let's see. Manganese sulfate is here. So what is the charge for sulfate? Sulfate SO4 2 minus. So hence pretty sure that in order for pretty sure that manganese will have to be plus 2. Okay. So a little side tip is that whenever I take a look at salts, right, it always has two components, your positive ions and your negative ions. So the charge needs to be balanced out. So this is plus 2. Okay. So this is why the oxidation state is plus 2. Now have a look at hydrogen peroxide. So where is hydrogen peroxide? Hydrogen peroxide is here. Now hydrogen peroxide, so we know that we want to know the oxidation state in hydrogen peroxide. So hydrogen Hydrogen has a state of +1. So oxygen in this case will be a -1. Okay, so let me present this properly for you guys. So if hydrogen is +1, so you have 2 + 1. This has to be something 2, which has to be -2, so that it equals to 0. That is how we usually look at how we calculate the oxidation state. Okay, part B. Using information in part A to explain why aqueous potassium manganate is an oxidizing agent. Okay, let's see. Most students will have issue with oxidizing agent. So what is oxidizing agent? Oxidizing agent is something, okay, something, some chemical, some whatever, something that causes another chemical to oxidize. Okay, so let's take a look. In this case, let's see whether there's any oxidation. So, very obvious, your oxygen has oxidized from -1 to 0. Okay, so in this case, yeah, in this case, this is 0. All right, so therefore, and how does it oxidize? Because potassium manganate causes the hydrogen peroxide, the oxygen in hydrogen peroxide, to oxidize. Hence, we say KMnO4 is an oxidizing agent because it causes the oxygen in hydrogen peroxide H2O2 to oxidize and increase oxidation state from -1 to 0. Okay, quite straightforward. Alright, so question 4. An ice cream maker from the olden days relies on crushed ice and salt as refrigerant coolant to keep his ice cream cold. However, he was confused on which salt, lithium chloride or sodium chloride, to make the refrigerant coolant. The table below shows the enthalpy of the solution of two salts. The enthalpy solution of the substance is the enthalpy change when 1 mole of substance dissolved in water. Now, using the above data, compare and contrast both salts. Recommend a suitable salt to make refrigerant. Now, first of all, what is refrigerant? Refrigerant means you need something to make it cold because you want to make ice cream. Okay, so not pretty straightforward answer. I would really straight away I know the answer will be this. Okay, so why is this? It's because we have an enthalpy change of plus of a positive. Now, what does it mean by enthalpy change? Enthalpy change means that if you are viewing yourself from a point of view of calcium chloride in this case. Okay, so what it means by you have a positive 4.3 kilojoules per mole of enthalpy change. It means that from the point of view, imagine this is you. So let me personify calcium chloride. So imagine this is you. You look from the outside, so the surrounding. So my surrounding gives you 4.5 kilojoules of energy. Okay, so in other words, you or calcium chloride gains the 4.3 kilojoules, And when you gain 4.3 kilojoules, what happens to the surrounding? The surrounding actually loses energy. So what is surrounding then? So surrounding is like the air around the calcium chloride, which means is the refrigerant. Okay, so therefore the air around the refrigerant or the air around the crushed ice will decrease in temperature because the energy in the air goes into sodium chloride. Alright, so I mean I spent a little bit more time to explain this so that those who still at this stage, almost 1 month until your O levels, still do not know how to differentiate exothermic and endothermic reaction, I hope it can really help you in this very last minute revision. Okay, so the answer will be NaCl, because the reaction with ice is endothermic. Okay, endothermic means enter. Alright, so energy enter NaCl, so it's endothermic. Hence, it is able to cool the surrounding air. Okay. So endothermic. Okay, not good enough. Hold on. Let me erase this. Endothermic as the enthalpy change is positive. Okay, so hence it is able to cool the surrounding air. All right. Okay, moving on. Okay, so calcium nitrate is a soluble salt used in wastewater preconditioning for odor emission prevention. Using standard laboratory apparatus and reagent, explain how you obtain the dry crystal of calcium nitrate. Okay, so I noticed that a lot of students also have this issue on salt preparation. Actually, salt preparation is very easy. Now, so we have calcium and we have nitrate. As usual, I will always split them into two to see, which means that so as usual, I will always split this into two. You need nitrate, and then you need your calcium 2+. Now, then you will ask yourself, how can I get calcium 2+? Now, you can get calcium 2+ in a few ways. Okay, you can get calcium 2+ in a few ways. You can get it from CaCO3. You can get it from CaOH, which is your lime water calcium hydroxide in the lab. Or I don't recommend using this. They don't accept. You can actually just react. You can just use calcium metal. Now, how do you get nitrate? How do you get nitrate? So in your lab, there's only one, which is nitrate acid. Okay, let me use another color. Okay, H2NO3. So this is the ingredient. This is the ingredient I want. So first of all, we need to identify the reagent or the ingredient, so to speak. So a good analogy I always like to say is that if you want chicken rice, okay, you need rice plus chicken, right? If you want duck rice, then you need duck, rice plus duck. So if you want dark noodle, then you need a noodle plus dark. Okay, so pretty much if you want to create calcium nitrate, you need to make sure your ingredient must contain calcium and must contain nitrate, which is why we chose these two. Okay, now I have already listed 1, 2, and maybe possibly 3, maybe not. I stress, don't use number 3, they will mark you wrong. So you have 1 and 2, which one should you choose? Really, it's up to you. There's no right or wrong answer, but it depends on what you choose. Your answer may be different. So I will spend a little bit more time to explain what it means why the answer will be different. So let's say now I choose calcium carbonate and nitric acid as a combination. So reagent will be your calcium carbonate and nitric acid. Okay, these are commonly found in your lab. So in this case, which method should we use? We will use adding excess. Okay, if you take a look at textbook, you have this method called adding excess insoluble substance into an acid. So we will add. So the method will be add excess calcium carbonate with HNO3, followed by you filter. So this is step number 1. Step number 2, you filter the mixture that. So you filter the mixture of these two added together, which actually when these two comes together, right, CaCO3 plus HNO3 should give you CaNO3 2 plus CO2 plus H2O. So now this one here is aqueous, and this one here is a liquid. This is a gas, so it will escape. So when you add, when you add the HNO3 into your calcium carbonate. Okay, so what happens is that since calcium carbonate is in excess, so you will need to filter so that it ensures that every single HNO3 will be fully reacted. Okay, filter the mixture and the filtrate will be collected. Okay, now what is the filtrate? The filtrate is actually, the filtrate of CaNO3 and H2O water will be collected. Now, what is step number 3? Step number 3 is that because you only want salt, okay, you only want the salt, CaNO3, you do not want the water, okay, you don't want this. So what you do, step number 3 will be to add them on a evaporating dish, okay, to heat until saturated solution. Okay, because they want crystal. Now, the important part is this keyword saturated solution, because without saturated solution you cannot get the crystals. They want crystals. If you don't want crystals, you can heat all the way until it becomes some dry powder. Okay, so the keyword is saturated. And then step number 4, let the saturated solution cool. And that's how you get the dry crystals of calcium nitrate. Alright, so now if you were to choose calcium hydroxide with, if you were to choose this, right, this combination, calcium hydroxide with calcium nitrate, right, then we cannot use this answer. We will have to use titration as the method to get the salt. So in this video, I don't want to talk about how to use titration. You can read it up on your textbook and or your notes. I believe you will know what to do. Okay. So basically, what I'm trying to say here is it depends. There's no one right answer, or so to speak. It really depends on the kind of starting reagent that you choose to select, and then from there you have to decide which is the correct method to get. And in fact, you only have 3 methods: precipitation, titration, and adding excess insoluble substance into acid. Okay, so in this case, we are using what we call the method 2 instead of titration. Okay, because of the starting reagent that I selected, which is calcium carbonate, a solid, and then nitric acid, a aqueous solution. Okay, so take note, I spent a little bit of time here. Alright, question 6 is on electrolysis. Okay, so for electrolysis, you have positive, negative. So for electrolysis, let's take a look at what happens here. So you have your, in this case, let's take a look at the electrolytes here. So the electrolyte contains silver ions, nitrate ions, OH minus ions, and H plus ions. So over on the other side, because it's a solution, you have your copper 2 plus ions, sulfate ions, H plus ions, and OH minus ions. Okay, so oh, what happened? Sorry, hold on, give me a second. Okay, so basically this guy repeats the experiment a few times, using the same concentration of copper 2 sulfate and silver nitrate, but change the current passing through the solution. He ran each experiment for 10 minutes, and at the end of 10 minutes, the student weighs the mass of each electrode. Okay, basically this one and this one. Okay, so and then the result is as shown on the graph. Okay, so sorry. Describe the relationship between the current and the increase in mass of the negative electrode as shown by the graph. Okay, so what the graph shows is that as the current increases, the mass of the electrode increases. Okay, so just take a look. You see, when you increase current, the mass just increases. All right, quite straightforward. Use the graph to predict the increase in mass of the negative electrode in the copper sulfate solution if the experiment is carried out using an electrical current of 2 ampere for 5 minutes. Now, so let's take a look at 2 amperes and let's see what is the value. So the value here is 0.4. I hope everyone can see. So let me zoom in a bit. So let me restart. Okay, so at 2 ampere, my mass increase for the copper electrode will be 0.4. Now, take note, because this is for 10 minutes, and so if you run this experiment for 10 minutes at 2 ampere of the current, then you will get 0.4 grams increase in mass. Now, this is the trick part. You are using 2 ampere for 5 minutes, which means your mass will be 0.2 grams. Okay, this is a trick question, so do not just rip off from the graph and say that the mass is 0.4. Okay. So during electrolysis, copper and silver are deposited on the negative electrode. With aid of ionic equation, account the difference between the masses of copper and silver formed given the same amount of current is used. Now, so I will use this to help. So what happens is that because negative n, if you learn your physics, negative n, this is where the electrons go. So the electron will come here. So the electron flow this way. Electron flow this way, electron flow this way. Okay. Alright. So what happens is that when the electrons comes here, so when the electron is here at the electrode, right, it will give the electron to the silver plus ions. And in this case, your silver plus ions, Ag plus E, will give you your silver metal, which is why it increases the mass. Likewise, on the other end, your electrons come in here, so come into come into this electrode. So the electrons is given to copper 2 plus, so Cu2 plus. Now, one electron is not enough. Copper needs 2 electrons, so Cu2 to give you Cu solid. Okay, so essentially I just explain and give you the 2 ionic equation. So the 2 ionic equation is as such. So we have copper 2 plus 2E minus to give you copper solid, and then you have silver plus 2E, 1E to give you your silver solid. Now, so that's not the end. And so what does it mean? Okay, so what does it mean? So with this ionic equation, right, this means what? This means that for, I'll write in red. So for every 1 mole of electrons, okay, for every 1 mole of electrons, what happens? Okay, for every 1 mole of electrons, 1 mole of silver is produced, and half a mole of copper is produced. Okay, because if you take a look at this mole ratio, copper needs, for every 1 mole of copper, you need 2 moles of electrons. So if you only have 1 mole of electrons, you only produce half a mole of copper. So this explains why, this is the first step to explain why there is less copper produced. Okay, as shown is this graph, whereas you have more silver produced. But this is not the only reason, because we also need to take into account that you need to remember that mass is equals to mole times mR. Okay, mass is equals to mole times mR. So that means to say, on top of the fact that the mole plays a part in affecting the mass, the MR also plays a part in affecting the mass. So what do we notice? We notice that the MR of copper is 64. Okay, look up your periodic table. And the MR of silver is 104. So this means, so what does this mean? So this means that 1 mole of electron, okay, will produce 1 mole of silver to produce 140 grams of silver, which is 104 grams of mass. But 1 mole of electron will produce half mole of Cu to give you only 32 grams of Cu. So can you see that copper is being penalized, so to speak, on both ends, on the number of moles and also by the fact that the MR. Okay, so you need to have, that's why the answer is 3 marks. You need the two equation, and then of course you need to talk about the fact that they have different MR, which explains why they produce different mass after a certain time going through electrolysis. Okay, question 7. The atmosphere of a planet from another solar system was analyzed, and it was found to contain nitrogen, carbon dioxide, oxygen, argon. The following setup was used to determine the volume of oxygen in the atmosphere. Okay, so the volume of air used for the experiment was originally 1000 cm3, while the original mass of copper used was 5 grams. After the experiment, copper turning was separated from black solid formed by dissolving in excess hydrochloric acid. The mixture was filtered and obtained, and the turning obtains as residue weigh 3.4 grams. So what happens here is that at first we have 5.0 grams. So what happens is that if this gas stream actually contains some O2, so what happens is Cu plus O2 will give you CuO. Okay, so the oxygen will react with your copper to give you your copper oxide. Now, so but however, this copper turnings, right, after the reaction, right, you will have two. You have copper oxide and you have copper. Now, what they do is this. They are using this and then they add hydrochloric acid. Right? So, when you add hydrochloric acid, the next question is, which one will hydrochloric acid react? So, the only answer is it will only react with this. As I mentioned earlier, copper do not react with acid, and hence the leftover, okay, so the residual weight, the leftover 3.4 grams is your copper. Okay, so the 3.4 grams is the copper, and which means that 1.6 gram of copper is reacted by the air. So write the balance equation. I rewrote the balance equation. Copper plus O2 give you CuO. Alright, quite simple. Calculate the number of moles of copper reacted with air. Now, like I said, you need to know this. Okay, so quite straightforward. So sorry, 1 second. Alright, we are back here. So okay, so as I mentioned, 1.6 gram, 1.6 divided by 64, you get, hold on, I need my calculator. (1.6 divided by 64), 0.025 moles. Okay, so done. Calculate the volume of oxygen reacted. Now, sorry, I need to adjust my balance equation. It wasn't balanced just now. So my mole ratio is copper is to oxygen. Okay, it is 1:2. Oh, sorry, wrong. 2:1, right? And then, therefore, we have copper is 0.025, and hence this will be 0.0125 moles. And to find the volume, now in this case, this question is not very good because it did not say that it is whether it is in room temperature or not. Okay, so it did not say that whether it is in room temperature, but in this case we will assume. So therefore, then from here we know the number of moles of oxygen, so we can find the volume of oxygen. So it will be 24 times 0.0125. Okay, we assume at room temperature. Did they say room temperature? No, they did not say. So we have to kind of assume. So so 1 mole of gas, of any gas, will occupy 24 dm cube of volume at room temperature. Okay, so 0.125 times 24, 0.3 dm cube. Okay, now, so calculate the percentage oxygen present in the planet's atmosphere. So we use 1000 cm cube. So in this case, 0.3 dm cube is actually 300 cm cube over 1000 cm cube times 100%, you get 30%. Okay, so 30% of oxygen is present in the planet's atmosphere. The reactivity of some metals can be compared using, sorry, let me repeat. Question 8, the reactivity of where is it? Okay, sorry for the glitch. The reactivity of some metals can be compared using the data in the table. So we have mercury, we have magnesium, we have nickel, we have zinc. So from this data, so question A, using the data from the table, arrange a metal in increasing order of reactivity. So how we can do this is by looking at which metal can displace the other metal. So let's see. So zinc can displace nickel. So zinc is more reactive than nickel. And nickel can displace your mercury. So nickel is more reactive than your mercury. And magnesium can displace zinc. So this is my order. Magnesium more reactive than zinc, zinc more reactive than nickel, nickel more reactive than mercury. But they want it in increasing order, so will be Hg followed by nickel, followed by zinc, followed by magnesium. Okay. The solution containing zinc nickels are green. State what you expect to observe when magnesium is added to nickel nitrate solution. Okay. So nickel nitrate when you add magnesium. So because magnesium is more reactive, so magnesium more reactive than nickel. Okay, magnesium more reactive than nickel. So it can displace. So what you're gonna say is that the solution will turn colorless, and silver PPT can be seen forming. So what is happening is that we have a solution, a green solution. Okay. So we have a green solution. All right. So this green solution is your nickel nitrate. Okay. So this is your nickel nitrate. Now when you add magnesium, so magnesium will displace this, so hence this is a displacement reaction. You get a solution like this. Okay, so this is aqueous plus nickel solid. So what happens is this. So remember the solution, right? This solution here, this solution is green. So when magnesium displaces the nickel, this solution now becomes magnesium nitrate instead of nickel nitrate. And magnesium nitrate is colorless, right? So what you observe is that they slowly change color. Not change color, but it turns pale. Okay? And then you will observe that they are nickel metal form. Alright, that's what my answer is trying to say. Write an ionic equation to explain for the write an ionic equation for the reaction in the part Bi, including state symbols. So I have already kind of written it. So nickel 2 plus Mg will give you Mg 2 plus I. Okay, so solid. Alright, so solid aqueous because they want state symbols. So in this case, aqueous, solid, and solid. Okay, yep. Alright, so this is how you write the ionic equation. Moving forward, steam was passed through the apparatus as set up as shown. So you have tube A zinc powder, tube B nickel oxide powder. A gas is produced when excess steam reacts with zinc powder. Describe a test to identify the gas. So zinc powder reacts with steam. Okay, so zinc react with steam produces, so zinc plus, okay, will give zinc plus H2O will give you zinc oxide plus hydrogen gas. So H2 gas is produced. So how do you test for hydrogen gas? Quite straightforward. Light it with a glowing splint and a pop sound, and it will extinguish with a pop sound. Okay, this one quite straightforward. Given a nickel lies between iron and lead in the reactivity series, state and explain what you would observe in tube B. Okay, let's see. Okay, so now what you need to know is that iron, right, and lead, okay, so both when you add with hydrogen, you can reduce it. Okay, so let's say we have iron oxide plus lead oxide. Okay, both of them will be able to be reduced to give you iron solid and lead solid. Okay, so if nickel lies between this, it will also behave the same. Okay, that means it is the reactivity is somewhere is in between, so it will also do the same. All right, so what we are gonna say is say and explain what happens to tube B. So tube B, because hydrogen is being produced, all right, so the hydrogen will react with the nickel here, and we will say that the nickel, hold on, oxide powder, let me see if they say, then let me see if they mention the color of nickel powder. Ooh. Nickel powder, okay, is green. Okay, so nickel powder is green because when nickel react with steam, it gives you your a silvery solid and it turns green, so that means nickel oxide is green. Okay, so the nickel powder will be reduced. Okay, so the green powder, okay, what is the green powder? The green powder is your nickel oxide. So let me help you. Nickel oxide, okay, will turn silvery. Now, silvery is what? Silvery is your nickel. Okay. All right, moving on. Question 9. Electrolyte simple cell. Okay. So the simple cell shown below use copper and zinc plates immersed in copper 2 sulfate and zinc sulfate solution respectively. The two half cells are separated to prevent side reaction and reach maximum voltage. Hence, it is connected by salt bridge, a porous membrane which allows ions from zinc half cell to pass to copper half cell and vice versa. Describe the observation at the zinc and copper electrode respectively. So what happens is that because in this case your zinc, so zinc is more reactive than your copper. Okay, so what happens is whenever zinc is more reactive than copper, it will lose electrons and give electrons here. So what you are going to observe is this. So in this case, we need to look at what is inside copper 2 sulfate. So copper 2 sulfate, you have your, okay, not good. You have your copper 2 plus, SO4 2 minus, OH minus ions and H plus ions. So when the electrons come in contact with copper 2 plus, it will cause the copper 2 plus plus 2E minus to give you copper solid. So what you observe is that at the copper electrode, right, copper electrode will increase in mass. Okay, you only need to describe, no need to explain. But for this walkthrough, I purposely explain so you guys can understand what's going on. So likewise, because zinc loses electron, okay, it gives out electron, the zinc solid will dissolve. So the zinc here, right? So zinc solid will dissolve to give you a zinc 2 plus ions. Okay, 2 plus. Alright, so it will give you zinc 2 plus 2E. Oh, what happened? 2E minus. Okay, anyway. So what we will say is that zinc electrode will reduce in size. Okay. Okay, suggest and explain which electrode is a negative electrode. So the answer is zinc electrode is negative. Okay, why? Because zinc is being oxidized and releases electrons. Okay, so how do we determine whether which electrode is negative or positive? The one that gives electrons. Okay, the one that gives out electron will be negative. The one that takes in the electron will be positive. So that's how we define which is negative electrode, which is positive electrode. Explain what would happen if two half cells are not separated but immersed in the same copper sulfate solution. Now, what happens is that we have this bath, okay, of CuSO4, and then we have your zinc, and then we have your copper. Okay, now what's going to happen is this tests your understanding or tests whether you remember that zinc is more reactive than copper. So in this case, what happens is that zinc will displace copper, and then copper will be produced. So what happens is that you will say that zinc being more reactive than copper, it will displace the copper in copper sulfate solution. Okay. All right. So this will reduce the voltage of the simple cell. Okay. Okay, question 8. Question 10. A student had 4 test tube samples A, B, and C, each containing exactly 6.2 grams of zinc carbonate. The equation of thermal decomposition is as shown. He was instructed to heat and weigh each sample. Each sample was then reheated, cool, weigh 3 times more. The student made a number of errors during the temperature. The result he obtained are given in the table below. Okay, quite a mouthful, lengthy question. Okay, so calculate the mass of zinc oxide formed from the decomposition of 6.2 grams of zinc carbonate. Now, very tempting. Very tempting as to what it means. If you were to take some time to study, you are very tempted to say that the zinc oxide form is this. Okay? Very tempting because you recognize that, okay, if I decompose, so let's say I have 6.2 grams here, all right, it will decompose, so some part of the gas will escape. So what is left is 4 grams. So it's very tempting to just put your answer 4.0. And that's where I suspect most people will struggle here. But no, this is not the answer. So what you should do is really calculate the solution. So let's see how to go about doing it. So we have the equation zinc carbonate to give you zinc oxide. So 1:1. So let's find the number of moles of zinc carbonate. Okay, so number of moles will be equals to 6.2 divided by will be mass over mR. So let me zoom and have a look at the periodic table. Okay, so here we have zinc. Where is my zinc? Zinc. Oh no. Zinc. Where's my zinc? Okay. Zinc 65. Okay. Sorry, my mind isn't working very well. As you can see, it's 3 a.m. in the morning. Okay, so anyway, let's get going. So you have 6.2 divided by what is the mR of zinc carbonate? So it's 65 plus 14 plus 3 times 16. Okay, so let's see. So when you calculate this will be 65 plus 14 plus 16 plus 16 plus 16. 6.2 over 127. 6.2 divided by 127 equals to 0.0488 moles. Okay, and then the mole rate, so you will also get 0.0488 moles of zinc oxide because the ratio is 1:1. So mass will be equals to mass of zinc oxide is equals to 0.0488 times the mR of zinc, which is 65 plus 16. Okay, times 3.954. So it's equals to, did I make a mistake? Okay, 3.95 grams. Okay. Okay, which sample set obtains the weighing error? So let's study the data. Let me see. Okay, it will be sample D. Why is that so? Because how can you have a thermal decomposition, right? That despite having so by right you are supposed to, the endpoint mass should be around 4 grams. Okay, 3.95 as we have calculated. But how can we say that there is no if you have 5.7 grams of mass before and after, this means that number one, either you have not hit it, or number two, there is some error in your second attempt. That means the mass of the second attempt. So we will say that D, as there is no change in mass between the second and first attempt. Okay. Explain why there is no further change in mass for third and fourth attempt in sample A, C, and D. So why is that so? Okay. Why is that so? Is because by the third attempt, by the second attempt, okay, all the zinc carbonate has already been fully decomposed. Okay, that's all. The student decides to investigate the thermal stability of carbonates of three metals, copper, sodium, zinc. He heats each carbonate in a test tube and bubbles the gas given off through lime water. State the results that he should record. Okay, now there's a few ways you can record the results. Number one is time. So what happens is that, let's say I have a test tube, I have some sample here, and then I heat it. Okay, I heat it. Now you can heat it until okay, you can heat it until you observe some bubbles form in the lime water. Okay, CaOH. Okay, so you can measure the time it takes to reach that state where you can see the bubbles here. Okay, where you can see the bubbles here. Now that's one way. Another way you can do is measure the temperature. Now this may be a little bit hard, so I don't really recommend, because it is quite difficult to measure the temperature of this. Okay, so what I will recommend is record the time. So record the time. Why is that so? Although we learned that it is temperature that results to decomposition. Okay, but the longer I heat, the higher the temperature this will be. So that is the relationship, which is why we say that we record the time instead of the temperature. Because if you want to record the temperature, you may accidentally record the temperature of the flame. Okay, so imagine I try to measure using like a thermometer here. I may accidentally measure the temperature of the flame instead of the sample. Okay, so it's better that we record the time. So describe how he can use this result stated in part BI to place the metal carbonate in order of thermal stability. Now, the more stable the carbonate, the longer it will take before it decomposes. Okay, because the more stable it is, the higher the temperature you need the carbonate to heat before it decomposes. So I repeat, the longer the time, the higher the temperature you will get before it starts to decompose. Okay, so what we're gonna say is that we will say that the longer the time taken for each carbonate, the more stable the carbonate. So in other words, what are we trying to say is that we can rank the time. Okay, so you can rank how long it takes for each carbonate to decompose. So the shorter it is, the less stable it is. The longer it is means the more stable it is. Okay. Okay, now we are on section B, free response question. So for free response questions, same for physics or and chemistry, both of them, right? You really need to read every single word of the data because that is where you can get some of the clues. Sometimes the answer is literally in the data. Sometimes you need the data to help you answer the question. So spend a little time on the data instead of just quickly jumping through the question. Okay, so let's take a look. So in short, there are two fuel cells device that converts chemical energy from fuel to electrical energy, commonly through reaction with oxygen. So here we have alkaline fuel cell and zinc air fuel cell. So for the alkaline fuel cell, in the paragraph it mentions that hydrogen and oxygen are mixed to give water and electrical energy using porous carbon electrode mixed with nickel nanoparticles and aqueous alkaline solution as the electrode. Okay, so take note, alkaline solution as the electrode, and then we have electrolyte, sorry, and then you have your carbon electrodes, right? And then for zinc air fuel cell, the electricity is generated between the reaction of oxygen and zinc using alkaline electrolyte to produce zinc oxide and electricity. Okay, so and then we have the diagram, and then they say one major issue with both fuel cell is electrolyte degrade caused by precipitation of metal carbonate crystals when hydroxide ions in the electrolyte react with atmospheric carbon dioxide. Okay, so this is another one. Okay, so the table below shows some information about the two types of cell. Working temperature alkaline fuel is 150 degrees Celsius. Zinc air is 40 degrees. Energy density is 300 for alkaline fuel. Zinc air is 1300. Okay, so let's see. In both fuel cell, it is important that carbon dioxide from the air do not pass through the porous electrode in both fuel cell. Explain why. So, as I mentioned, the paragraph will tell you. So they already said here. All right. So what you're gonna say is that the carbon dioxide will react with the hydroxide ions to produce a hydroxide ions to produce what? To produce a metal carbonate. Okay. okay, which will degrade the simple cell, reducing the voltage. Now, so basically, question A, you cannot answer it without reading the question and without reading the data. So it is something like your comprehension. Okay, so part B, write down the ionic half equation for the reaction that occur in the cathode and anode of alkaline fuel cell. Okay, so we need to focus here. And let's take a look at the diagram. It may give us some clue. Let me see. Okay, we only know that the hydrogen and oxygen combine to give water. Alright, so now, okay, so I think I saw something. So alkaline solution, so that means my electrolyte will contain OH minus, and probably because it's a solution, it also contains H2O. Yeah, I think pretty much that is it. Otherwise, so that means to say over here it also contains H2O. Now, so let's see. At the cathode, I'm just guessing oxygen reacts with the... You see, you can't have oxygen react with OH minus. Okay, I don't think it produces anything. So my best bet will be, yeah, because no, so far what can you form with oxygen and hydrogen OH? Probably you can get water, but I don't think you can balance the equation. There's no way. So yeah, this is not possible. So the only other way I can guess will be the oxygen at the cathode will react with your water to give you OH minus, and also to give off plus electrons. Let me rewrite this, sorry. So your OH, O2 plus H2O plus, I don't know how many electrons will give you OH minus. So let's balance this equation. I think it's 2 and 4. So 4E. Now, how do I know that it is 4E? Because of this idea called conservation of charge. That means on my left hand side, I have 4 negative. Hence, on my right hand side, I must also have 4 negative. Okay, so left hand side, right hand side, both has the same number of charge. 4 negative on the left, 4 negative on the right. So even conservation of mass is in place. On the left hand side, I have 4 oxygen. On the right hand side, I have 4 oxygen. And likewise, on the left hand side, I have 4 hydrogen, and the right hand side, I have 4 hydrogen. Okay, so in this case, I'm quite confident this is my answer. Okay, plus 4E to give you OH minus. Okay, now at the anode, they already see, if you can zoom in, right? So the hydrogen come in, the OH minus go to this electrode. So quite obvious, the hydrogen will react with the OH minus. So hydrogen plus OH minus to give you, yeah, in this case we can only get water plus electrons. So let's see how many electrons. But first we balance the equation. Let's see, let's put a 2 here. We have 2 here. Yes, it's balanced. Oh, it's balanced, hence this is 2E. Okay, so done. Other than fuel storage, fuel cell cost and maintenance give another advantage of zinc air fuel cell instead of an alkaline fuel cell. So again, you are not going to learn this in textbook. You need to take a look at the data. So in this case, manufacturing they don't want, storage they don't want to talk about. So what else can we talk about? We can talk about this. So very obvious, zinc air has a higher energy density. So zinc air has a higher energy density. Okay. Then alkaline fuel cell. Okay. A student commented that producing energy from both fuel cell is non-polluting. Do you agree? Now, very tempting to say that they are non-polluting because let's see here. For alkaline fuel cell, it gives you, my end product is water, very clean. For zinc air, let's see what it produces. Okay, it is renewable. The zinc oxide can be converted into fresh zinc using electricity. Now, so do you agree? Now, despite the fact that the waste is only water and zinc, it doesn't necessarily means that by producing this electricity, right, using this fuel cell, it is non-polluting. Now we need to consider what? We need to consider how are we going to produce oxygen? How are we going to produce hydrogen? Right? Likewise, how are we going to produce the electricity to get back my zinc, okay, from the zinc oxide? So what they are trying to say here is that it is renewable because my zinc oxide, okay, can be converted into zinc using electricity. So there's a lot of question. Really, is electricity clean? Questionable, okay? It may be clean, it may not be clean. It can be clean or not clean. So not clean in what sense? If you use coal powered power plant to get your electricity, then the electricity is not clean. So in a sense, this zinc air fuel cell is not clean. Okay, it's not pollutant free. But of course, you can also argue that if my electricity is coming from wind, solar, etc., then you can say that the electricity is clean and this entire zinc air fuel cell is environmentally friendly. Okay, but how about hydrogen? So we have also the same idea. How do we get hydrogen? So typically we get hydrogen from the refineries, or you can get hydrogen by conducting electrolysis of water. So again, it comes back to the question, how do we get the electricity? So in that case, right, I would argue, okay, right now I'm quite sure that at least 80% to 90% of our electricity comes from burning of fossil fuel. So I would say no, okay, do not agree. Why is that so? Because the electricity to produce the zinc and oxygen, zinc, oxygen, and hydrogen may not come from non-polluting polluting sources. Okay. All right. Write the overall equation for the reaction in the zinc air fuel cell. Okay, so let me see. Zinc air fuel cell, you have a zinc, let me see. Zinc, oxygen, so my answer is here. It reacts zinc, oxygen with alkaline to give you zinc oxide. So quite easy. So in this case, it will be zinc plus O2 to give you your zinc oxide. Okay, quite easy. Calculate the energy density per mole of fuel for zinc air in watt-hour per mole. Whoa. Per kilogram watt-hour. Okay. Okay, hold on. I have some technical glitch. Okay, so let me write. Okay, so in this case, so we have a solution. So 137. 1 watts okay, 137 watts. 37. Okay, I'm sorry. There's so much technical glitch. Okay, so basically you have 137 watt hours per kg. Okay. Now, how do we convert it into watt hours per mole? Which means that this thing must convert into something per mole. So you have kg. How can kg convert into mole? Okay, pretty much this is mass to mole. How do we change mass to mole? It's quite easy. So what they are trying to say is that 1 kg produces 137 watt hours. Okay, now, so but 1 kg of zinc, okay, okay, so 1 kg of zinc, right, has how many moles? So it's 1000 grams divided by 65. So you have moles of zinc, okay, which also means that what? Which also means that 115.38 moles of zinc gives you 1370 watt hours of energy. Hence, how do we find 1 mole of zinc? Because they want per mole, means energy per unit mole. Okay, unit means 1. Okay, so 1 mole of zinc gives you 1370 divided by 15.38. Okay, let's see what we have. 1370 divided by 15.38. We get 89 watt hours. So this is my answer. Okay, per mole of fuel. So what is the fuel we are talking about? We are talking about your zinc electrode as the fuel. All right. Okay. So the answer is 89 watt hours per mole. All right. Okay, question 12. 3 experiments were carried out to study the speed of reaction between dilute acid and magnesium ribbon. The table shows the amount of acid, mass of magnesium ribbon used, drop of copper sulfate used, and the time taken to collect 15 grams of hydrogen gas for each experiment. Explain in terms of collision theory why the time taken for experiment 1 is shorter than experiment 2. So let's study experiment 1, experiment 2. So what is the difference? Spot the difference. This is hydrogen, sulfuric acid. This is hydrochloric acid. So sulfuric acid is H2SO4. Hydrochloric acid HCl. Now why do I say that? Because in HCl there is only 1 H plus, whereas H2SO4 has 2 H plus, which means based on our collision theory, right, although we have the same concentration of acid, but in this case we have actually 2.0 moles per dm cube of acid. Okay, therefore, how are we going to explain? We will say that in experiment 1, there are higher concentration of H plus ions than experiment 2. This increases the frequency of collision. Okay, this increases the frequency of collision with the magnesium, and hence increases the increases the rate of reaction. So yeah, higher concentration. Okay, so I think I need to explain a little bit right in a little bit because H2SO4 has 2 hydrogen plus ions, while experiment 2, okay, HCl has only 1 H plus ions. Okay. Using the information from the table, explain the role of aqueous copper 2 sulfate in experiment 3. So let's see, let's spot the difference. So we are comparing sulfuric acid with sulfuric acid. Okay, everything the same except for this. So how can the time taken reduce? Very obvious. The only reason that you can think of is CuSO4 acts as a catalyst, which reduces the activation energy required by the reaction, hence increasing the rate of reaction. Okay. Okay. Experiment 1 was repeated using magnesium powder. Sketch a graph of volume of hydrogen gas produced against time taken for the experiment using both magnesium ribbon and powder. Okay, so with powder, you learn that in the rate of reaction, what affects rate of reaction: concentration, surface area, pressure. No, in this case, pressure is not. Pressure only works for gas. So I repeat: concentration, catalyst, temperature, and I think surface area. Okay, so these are the 4 factors that affect the rate of reaction. In this case, when you are using powder, it increases surface area. So if you are going to use powder, then let's just draw the base one. Okay, so this is 50. Why I know 50? Because they say this is 50. So this is, and then you label this as ribbon. Okay, and then you have the other one, same thing. Okay, and then you say this is powder. Okay, you need to show that the rate is, the gradient here is steeper, and also it reaches the reaction ends earlier. All right, so this is your 3 marks. One mark here, 2 mark here, 3 marks here. Okay. Further experiment of the reaction between fixed mass of magnesium and excess sulfuric acid were carried out. In this experiment, various volume of aqueous copper 2 sulfate were added to sulfuric acid. The graph shows the volume of hydrogen gas decreased with various volume of aqueous copper sulfate. Okay, so what you notice that the more aqueous copper 2 sulfate you add, right, the less hydrogen it produces. So why? We will see why. Predict the change in volume of hydrogen gas produced if aqueous potassium sulfate is used in place of aqueous copper 2 sulfate. Now, first of all, we need to understand why the volume of hydrogen will drop. Okay, again they are testing you on reactivity series. Why is that so? Now you have, okay, let me use another color. So you have your copper 2 sulfate solution. So what happens is that if you were to place a magnesium ribbon, so again you have this reaction, magnesium plus CuSO4, magnesium more reactive, so you get magnesium SO4. Okay, so the more copper 2 sulfate you add, the less magnesium you have. Okay, the more copper 2 sulfate you add, the less magnesium you have to produce the hydrogen when it is being reacted with sulfuric acid. Okay? In short, what I'm trying to say again is that magnesium will displace copper, and now you see your magnesium is now in the solution. So you don't have in order for you to produce hydrogen, right, you need magnesium plus H2SO4. Now no more magnesium. So what happens? Then no more hydrogen. Okay? Because it will produce hydrogen and magnesium sulfate. Right? But in this case, because all your magnesium has displaced copper 2 sulfate. And that's why you have no more magnesium to react, and hence no hydrogen gas produced. Now, so what happens when you use potassium sulfate? So magnesium plus potassium K2SO4. Can it react? No, because potassium is more reactive, so nothing happens. So what happens is that even if you increase potassium sulfate, right, the number of potassium sulfate, what happens? The amount of magnesium still remains the same. So we say that the volume of H2 gas produced will remain the same. This is because K2SO4, this is because magnesium is less reactive than potassium. Okay, hence it is unable to displace K2SO4. Hence the mass of Mg remains the same to produce H2 gas. Okay. Okay, now this is question 13E, so I will be working on both either and all questions, but in the exam, please only choose either one. Okay, so let's take a look again at question 13. Nitrogen was discovered by Scottish physicist Daniel Rutherford in 1972. It is the fifth most abundant element in the universe and makes up 78% of the Earth's atmosphere. So Haber process combined nitrogen from the air with hydrogen derived mainly from natural gas into ammonia. When ammonia is dissolved in water, an ammonia solution is formed. Okay, so what this is trying to say is that we have water. Okay, and then what we do is we pump in ammonia gas into this. And so this ammonia gas pump into the water here, it will form ammonia, you will form ammonia, aqueous ammonia. Okay. So what is the likely pH of this ammonia? So ammonia is an alkaline, but this is a weak alkaline. Therefore, we should choose something that is not 14, not 13, but somewhere anything that is less than 12. So I would like to put pH 11. Okay, so if a few drops of universal indicator is added to the ammonia solution, explain the color change that occurs. Now, so what happens is this: initially, when you only have H2O and you add universal indicator into it, the universal indicator will turn the water green because water has a pH of 7. Now, as I slowly introduce ammonia gas in, this water, like I mentioned, will become aqueous ammonia. Okay, and what's going to happen is the aqueous ammonia, because it is an alkaline, it will change the color of the solution from green to somewhere violet. Okay, so because of the change in pH, so our answer will be as such. The color will change from green to violet. Okay, so this is only 1 mark. You need to explain why, and the reason is because as ammonia gas is being added, it turns water into aqueous ammonia that has a pH of 11, changing the color. Okay, color of indicator. Okay, quite long, but it's okay. Now, ammonia has a strong smell. A beaker of aqueous ammonia was placed in the front of the class of a student. At first, the student at the back of the class could not smell the ammonia. After a few minutes, they could smell ammonia. Now, why is that so? So, first we need to understand that aqueous ammonia, okay, you cannot smell liquid aqueous ammonia. Now, then how do the student at the back manage to smell it? It must first evaporate. So the aqueous ammonia will evaporate to give you your ammonia gas. Alright, and what's gonna happen is that now you will have a region of high concentration of ammonia gas, and then this region here is region of low concentration, and you learn that gas will travel from high concentration to low concentration. So how are we going to answer this in words? So what you're going to say is the aqueous ammonia will evaporate. Okay, it will evaporate and turn into ammonia gas. This creates an area of high ammonia gas concentration, and we also need to recognize that gas and ammonia gas is able to move randomly in all direction. Now, with this statement, right, we are using kinetic particle model to explain why eventually the ammonia gas will travel backwards. Okay, it's because it can go in all directions, and of course, one of the direction will be going back to the class, and hence, the gas can diffuse to the back of the room. Okay? Yeah. So that's how we get 3 marks. Okay, question B. Ammonia is used in the manufacture of nitric acid. Balance the equation. So this should be quite easy. I have 4 nitrogen here, so it's 4. In total, I have 10 O, so 4 here, there will be 6. Okay, and then let's double check the number of hydrogen. 12 here, 12 here. Okay, good. Now, using ideas of so the reaction is exothermic. Using ideas of bond breaking and bond forming, describe what is exothermic. Now, first of all, in chemical energies for chemical energies, right? Bond breaking. Okay, when you break a bond, you take in energy. Okay, so bond forming. Once you form the bond, you release energy. Now, what is exothermic? So again, I will repeat. So exothermic means, let's say my gas, nitrogen, for example, the system, the reagent, okay, the chemicals. Exo means exit. Exo means exit. So what is exiting? Energy is exiting. So energy is exiting. Okay, because that means this reaction will cause energy to exit the system. Okay, the system will lose energy. So which is why we have a negatives, which is why exothermic reaction has a negative enthalpy change. The negative is to indicate that the energy is being lost by the reagent to the surrounding. So you are always looking from the point of view of the system being the reagent, okay, or the chemical, so to speak. So how do we use the idea of bond breaking and bond forming? So how can we have a negative energy output? Okay, so let's see my answer, and then I hope it should explain why. So we will say that the amount of energy released during bond forming is more than energy gain to break the bond. So what this means is that the energy in to break bond, okay, is less than. So if you net out the effect, is less than the energy out when bonds are formed. Okay, so whenever there's bonds formed, energy will be given out. Okay, so part 3, the NO produced in the first step then reacts with oxygen to produce nitrogen dioxide, NO2, according to the equation. Okay, state with reasons how this equation show which substance is oxidized. Now, there's 2 ways to answer this, you can talk about oxidation state, or you can use the fact that it gains oxygen. Okay, both are acceptable. Okay, which one you want to use is really up to you. For me, since this is a 1 mark, I will use this to explain. So state with reason. We will say that nitrogen is being oxidized because it gains oxygen. Okay, now some of you may ask me, how come sometimes sometimes your teacher mark you wrong when you use this as a reason, and sometimes you get this correct? It's because in this question they did not specify which method you need to use. So unless the question says that you need to use by means of oxidation state or by means of gaining or losing oxidation state, then we are restricted only to analyze a question by using this method to see whether nitrogen has increased its oxidation state or decreased in oxidation state, to suggest, to conclude that nitrogen has actually oxidized or reduced. Okay, so in this case, I just use the more convenient way, which is the fact that it gained oxygen, hence it oxidized. Okay, part C. Oxides of nitrogen are atmospheric pollutant. State one adverse effect of oxides of nitrogen on health. Okay, so take note, they say adverse effect on health. That means you cannot talk about things like acid rain, etc. You cannot talk about anything relating to the environment. You can only talk about how it affects the health. So how oxide of nitrogen affect health is that it irritates the eyes, okay, or lungs, whatever. Okay, so quite easy, you can get a 1 mark. Okay, now the last question, all question. So we have two graphs, graph 1 and graph 2. From the looks of it, pretty obvious this is on the topic of periodic table, and to be more specific, this is group 7 elements. So we have the atomic radii, and then we have the electronegativity. Now what is electronegativity? As you can read here, electronegativity is a measure of a tendency of atom to attract electrons. Okay, so what this means is that the higher the electronegativity, the more the ability for the atom to pull in electrons. Okay, and in this case we can see that fluorine has the highest ability to pull in electron, and we will see how it affects the reactivity and so forth. Okay, so let's see question A. Use the trend in graph 1, explain why atomic radii of halogens increases on going down the group. Okay, so now what do you remember about going down the group? When you go down the group, okay, when you go down the group, what happens is, so for fluorine, you have how many shells? Okay, if you take a look at a periodic table, you notice that fluorine has 1 and 2 shells, and hence this is what we call the atomic radius. Okay, so now for chlorine, will have 3 shells. So 3 shells, quite obvious, quite common sense to understand that if you have 3 shells, then of course you will have you should have a bigger atomic radius, and etc. for bromine and iodine. So if you take a look at your periodic table, you'll know that fluorine, chlorine and bromine, how are they differ? They differ by the fact that each of them has one more outer shell, one more electron shell than the other. So fluorine has 2, chlorine has 3, bromine has 4, iodine has 5, etc. Okay, so how are we going to explain the atomic radius. So we are going to say by we will say that the halogen down the group has more electron shells. Okay, so hence this increases the atomic radius. Okay, so basically essentially that's I'm just writing in words what I just explained here. All right. Predict the reactivity of halogen going down the group using graph 2 and explain the prediction using electronegativity property in graph 2. Now, by now, so near to exam, you should at least know that for group 7 elements, the reactivity decreases down the group. Okay, so there's no need to predict. This is either you know it or you don't. So I'll explain why, and the reason why it has got to do with this electronegativity properties. But let's just write down an answer. So halogen have reducing reactivity down the group. Okay, take note, group 7, as you go down the group, the reactivity decreases. However, for group 1, listen carefully, group 1, your sodium, potassium, lithium, group 1, the reactivity increases down the group. Now, so explain your prediction using electronegativity. So from here, we can see that this means that the halogen with lower electronegativity will have lower reactivity. Okay, so that's the relationship. Can you see? As you go down the group, the electronegativity decreases, and at the same time, we know that the reactivity also decreases. Now, why is that so? So how do chemical reaction occurs? So, for instance, how do you form NaCl? In order for you to form NaCl, right, the Na outermost electron must be donated to the chlorine in order to form an ion. Okay, so what is electronegativity? Electronegativity, as I mentioned, is the ability for the atom to attract the electrons. So yes, my sodium is giving away the electron to chlorine, but chlorine must also have the ability to attract this electron, so to speak. So if you have higher electronegativity, it means that it is easier for you to attract these donated electrons, and hence you can react way faster. And that's why with higher electronegativity, you increase the reactivity. Okay, so that's how in a gist it works. I don't want to spend too much time explaining this, because this is supposed to be a walkthrough of this paper. Otherwise, I will need need way more time and extend the video longer. Okay, so if there is still time or opportunity next time, I will perhaps create another video to explain this if someone requests for it. Otherwise, I will leave it as such. Okay, part C. Fluorine is the first element in group 7. A jet of fluorine gas is aimed at filter paper soaked with potassium bromide. Okay, so you have potassium bromide here. Potassium bromide. Alright. So what do you think will happen? How come? So they say explain why the solution turned brown. Now, potassium bromide has no color. So KBr is colorless. So how come when fluorine gas comes in contact with KBr, it changed to brown? It's because fluorine gas plus KBr, you have this reaction KF plus Br2. Okay, so what happens is, this is what we call the displacement reaction. Okay, so this is a displacement reaction. And how that occurs is because fluorine, the halogen, is more reactive than the bromide halide. That's why it can replace the position. And that's why you can see the fluorine now takes the place of bromine. This is called displacement reaction, where the more reactive halogen can displace the less reactive halide. Alright, so I just explained. So this is because the fluorine displace the bromide in the KBr solution. Okay, and bromine is brown in color. Okay, so the reason why the paper turned brown is because bromine comes out and bromine is brown. So you are seeing bromine. That's what this statement is trying to say. So write an ionic equation to support this. So ionic equation F2 plus Br minus equals gas to give you F minus plus Br2. Okay, should be liquid. Okay, then AQ 2. Okay, done. This is my ionic equation. Helium is an element that is not included in group 7 element. Draw ionic configuration at helium. Okay, so this is quite straightforward. Helium has a proton number of 2, so this marks is just giveaway. Hence, give a reason why helium is not included in group 7 element. So again, this is a straightforward answer. So it is not in group 7 because it does not have 7 outermost electron. Okay, but neither are you gonna say that this is this helium has 2 outermost electron. In fact, this you need to add one more statement just in case to prevent any misunderstanding, is that we will say that helium has a full outermost electron configuration. Okay. Hence belongs to group 0. Alright, some people think that the use of helium is to fill party balloons should be discouraged. Suggest a reason why they think this is so this is actually this question actually comes out in, I think, 2017 O-level paper, but the question is different. So unless you have done it, then you will understand the context, but I will just give you the answer. So one of the reasons is because the supply of helium on Earth is limited. Okay. The air, as our air does not contains helium. Okay, so yeah, the fact is our air doesn't only have nitrogen, oxygen, and carbon dioxide, and a little bit of argon, etc. But it doesn't contain hydrogen. It doesn't contain helium. So some of you must be thinking, then in that case, how do we get helium? Now, to get helium, one of the ways is that the Earth, right? This is our Earth. So because of during the history or the birth of Earth, right, you get air pockets of helium underground. Okay, which is trapped. So these are all helium, 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 helium. So what we can do is that we can drill down, okay, to all these air pockets to collect the helium and then store it in like a tank. And once you store it in the tank, then you will use it as and when you like. But the moment you release it, it will escape out of our Earth atmosphere and go to outer space, and it doesn't come back. And this is the reason why party balloons, right, is quite wasteful, so to speak, because every time you release the helium, it goes out to outer space for good. And the truth is, helium is very, very useful, much more useful than you can imagine other than party balloon. One other example is that helium is used in MRI. Okay, if anyone knows what's an MRI, it's a scan that uses magnetic resonance imaging. Basically, it's like an X-ray eyes that can see through, so to speak, your body and see how, if there's any tumors, etc. So that's one of the main useful use for helium other than in our party. Okay, so so we come to the end of this paper. I hope this will really help you guys in the exam in probably another 3.5 weeks. I will still continue to upload pure physics and pure chemistry paper, since somebody has already requested for it through my Instagram DM. So yeah, so please stay tuned, subscribe and like my videos, and I will really continue to upload all these videos up until your O-levels. Okay, so that's all for today. Okay, bye bye.